Okay, good. So I think this is even simpler than Kurt's presentation. So it's, and it actually starts with some very simple generalities about gravitational wave data analysis. But I think there are a couple of people in the audience who can probably use that. And for the others, you can go to sleep a little bit and then wake up again. And in fact, it is so simple that all while doing this, and still now, I wonder if it's not there hidden in some book, and I'm just confined to the wrong brain in literature space and just I don't know about it. So I'm pretty sure that if I post it to archive, I'll find out that a Russian did it in 1919, but then he died. And so, anyway, so I shouldn't have done that the other way. So what's wrong here? This thing kicks me out. It's interesting. Oh, okay. That's what happens when the last slide is the same as the first one. Okay. So a signal, a little sun Gaussian stand for your prototypical signal. It could be anything. And a signal is a function of some parameters, in this case the amplitude, the attenuation parameter, and a frequency. And parameters standing for science. And you'll notice the quotes. There's actually a blog that collects all incorrect uses of emphasis quotes, which are really humor quotes. And when I feel a little disillusioned about the state of gravitational wave science, sometimes I think that those parameters stand for science in the same way that in some cases when you get Italian food, it's tomato and olive. So, but still, parameters tell you how your waveform or how your function changes in space. And the nice thing is that I think I can basically explain gravitational wave data analysis with an addition and a subtraction. So the addition is a simple one, is the fact that you don't get with an experimental apparatus to actually measure the waveform that nature gives you, but there's noise on top of it. So this is for SNR of 5, so you can still see it kind of in here, that if you have edited noise, you add to this, you get your confused thing. And then the task of the data analyst is to do the subtraction, but you don't know in advance what you're subtracting, so you have your noisy data, you try out a few things, you get different of what should be noise or residuals, and now the thing that's least noisy, at least for well-behaved noise, is actually the most likely. So what you've subtracted that gives you the least noisy final residual is actually your maximum likelihood estimate. And it doesn't need to be the right thing. So in this case, for this noise, you go back to a waveform that's not quite what I started with, adding noise to it. So you can write the probability of your parameters, the known parameters of the underlying signal, as a probability over the noise residual. And you want to systematize this operation, do it for all possible value of parameters, and you get something that looks like a map. In this case, for this noise realization, I get the map on the right, where the contours are roughly the 1 sigma, 2 sigma, 3 sigma in, am I blocking you completely, Kurt? In 2 dimensions, and the pink dot is the maximum of this distribution, which is, again, it's not a 0, 0. These would be errors. This would be delta alpha and delta f actually in these 2 dimensions. So if there was no noise, I would find that the maximum distribution is here in the center, but there's a displacement. So that's just the frequentist error if you're a practitioner of this. Now, how do you do this in practice? Well, if you have just 2 parameters, you just run a brute force search. But if you have many parameters, many people like to use this Markov chain Monte Carlos, where you're basically using a random walk, a controlled random walk that moves around in parameter space, and that basically lays down points with a probability distribution that's the same as your likelihood. If you're doing Bayesian inference, there's also a prior that comes into it, but it doesn't really change things very much. Now, one thing that sadly we always have to realize is that we live in a pre-detection era. It's not pre-injection, but it's pre-detection. So when we think about how powerful an instrument is, we have to think about fictitious signals. And we don't really have data with a particular, we don't know what the data will look like with a real signal, so we have to consider the space of all possible noise realizations. So therefore there's not only one map like this, there's actually an infinite number of maps where all different noise realizations on top of the same signal give rise to different likelihood maps. And if you see with such a low, with an SNR of 5, which is low, but if I had more than 2 parameters, I may get in trouble already with a higher SNR. You get quite a variety of different shapes for your likelihood map. The pink dot is always the location of the maximum, so your maximum likelihood estimator for the parameters. So the holy grail, really, I want to characterize how powerful an instrument, a measurement of a physical scenario is with a certain detector, is to consider all possible noise realizations at once and basically do a Monte Carlo of Monte Carlos. Pretending to look for a signal with unknown noise and all different kind of noises. And a rough estimate, a typical estimate, is this is an exa problem. So it's not petascale, it's exascale, 10 to the 18, because a decent Monte Carlo maybe needs to visit 1 million points. You're doing a Monte Carlo, so that's another 1 million different noise realizations, and maybe, million point FFT, a little less than that if you add the n log n factor, so that's what you get. That's not impossible even right now. It would mean that if you have a petascale computer and you program it, you use all the parallelism, you could do this in 1,000 seconds, roughly. Still, petascale computers are still kind of expensive to get, and plus all of this is for one true parameter set, for one true source that's hidden in there. You may want to redo it for different signals. So I cannot get the holy grail. And I must tell you that I try very hard to find a useful snippet of the Monty Python movie to show you here, but I couldn't get one that was funny in the right way. So what's less than a holy grail is a grand challenge. Okay, usually doesn't go well when it's a grand challenge. So perhaps instead of characterizing the variation of all these distributions, we can just look at the distribution of the pink dot, so the distribution of the maximum likelihood estimator. And if you do it numerically, you can do it on one computer in Mathematica. You can tell it's numeric because it's shaggy. Yeah, it's a little. And this is, I've done 100,000 times. I've taken different noise realization. I've just run a search. This is just a gradient descent or something like that. The search and find out where the maximum likelihood estimator ends up. And then you find the map like this. It kind of looks like this map, but the colors are different because it's really a different kind of map. This is a map of the maximum of those other maps over all possible maps, like that. Why this is interesting? Because at least it tells you something about the distribution of your guesses, of your best guess for the parameters. And technically you would say this is a measure of the frequentist error of the maximum likelihood point estimator. Now you can do it numerically. But the idea is, can we do it exactly? If I could do it numerically, because actually I had a very small signal, I had a 60-point signal here. And I had only 2 parameters, so I could do brute force, just 40 by 40. I didn't need to do a million walk samples in a macro chain Monte Carlo. So can we do it exactly and do a little better? So if somebody is going to say Fisher matrix, I should say that Fisher matrix gives you a prediction, which is quite unlike this. I mean, yeah, it's kind of same order, but there are distortions, and those distortions may be interesting to you, especially once you go into more than 2 parameters. All of that will get worse. So Fisher matrix prediction look like this. It's actually very simple. You just compute one matrix of inner products of derivatives, and then it's just an exponential. So some of you may know this is one of my pet peeves, that the Fisher matrix cannot really do everything that people try to use it for. And I wrote a paper that was supposed to chastise, the use of Fisher matrices for SNRs that are not high enough, and all that. And I actually gave a criterion that you can use to check whether you have an SNR, your SNR is high enough to use the Fisher matrix. And to my satisfaction, I see that now everybody who wants to publish Fisher matrix paper cites my paper, saying, well, it may be a problem and you can do what it does, but they don't do it. They don't check, right? So PhD comics is always, in this case, an inspiration, because I can say that if I now go to the ensemble of all papers written over Fisher, half of them will be right, half will be wrong, and on the average, my paper has no impact on what they're doing. So that's how it happens. Anyway, let's move on to some math, because Kurt had a lot and I need to match him. So let's try to find the distribution of the maximum likelihood estimator from first principles. So log likelihood is the thing that we want to maximize. So this would be the signal, noise plus the true signal that's in there. Sorry, this would be the detector data, what you measure, minus your best model for the data. You want to maximize this. You do it locally. It's basically it's one derivative. You want to the derivatives with respect to all the parameters of this expression to be 0. It's quadratic, so you just need to do it on one side and you get something like that. Let's call this quantity the maximum likelihood function, and when this equation is realized, maximum likelihood function is 0. Nothing to that. Now, I can define a formal solution to the maximum likelihood equation, which is just the maximum likelihood estimator. But in principle, this is difficult to find. It takes something like a numerical search, unless unless the Fisher matrix regime applies, in which case everything is linear in the parameters, as in Kurt's case. Everything was linear in his parameters, so he could just invert the matrix and find the solution. But in the generic case, you have to look for it. So that's difficult. But if I knew how to do that, I could write something like that. Again, this is pretty formal, but the distribution of the maximum likelihood estimator is enumerating all possible noises with their probability. Is just a delta times this measure. There's nothing to this. This just means I'm looking at all noises. I count how many give me this maximum likelihood, how many give me a different one, and so on. Now, what's nice here is, however, look at this quantity here. This is a complicated function of the two parameters if the waveform is a complicated function of the parameters. However, this is a pretty simple function of the noise. It's a linear function of the noise, which means that if I know what maximum likelihood I want, it's easy to find all the noises that give me that maximum likelihood estimator. So I can take this delta here and rewrite it as an explicit delta, or implicit over this maximum likelihood function. There's a Jacobian involved, which is a derivative, but what this is saying is just that I don't need to know, instead of taking all the noises and looking what maximum likelihood estimator they give me, I can take all the maximum likelihood estimators, look what noise I need, and then count those, and basically do this, what's it called? It's the Stieltjes integral instead of the Riemann integral, right? Just do a kind of transpose of it. And now, thus I posit this is a general formula where I'm using a Gaussian noise distribution that will give you the distribution of the maximum likelihood estimator. And the nice thing that I'm going to show you in 2 slides from now is that this integral, although it looks bad because it still has this product, and you'd think that to make this product you have to actually write out 1,000,000 point noise realizations. This is actually not an n-dimensional integral. Actually, it's more than n. It's n to some power, right? All possible noises. This is a d squared dimensional integral, where d squared is where d is the number of parameters. But before I show you why this is lower dimensional, let me hammer on the intuition for what we're doing. Let's go to a very low dimensional model, which actually Kurt came up with, which is, my model is just a point on the unit circle. There's one parameter, theta tells me where I am. Noise is just 2-dimensional unit variance Gaussian noise, and then let's say the true signal is here at 1, 0. Therefore, this the shade here tells me what the likelihood is, actually the probability of a point of the signal being moved away by noise. So noise realization will displace me away, and the likelihood of this displacement is the color underneath it. Now, for this displacement, what's the most likelihood in value of the signal parameter? Well, it's the projection back to the circle, so it's this theta ml. And the point to this general formula is that I want to take this kind of sector and to because all the noises here give me the same theta ml, so I consider it theta ml. I look at this and I integrate the color. I integrate the blue and purple underneath. That's just what this integral is doing here. And if you're curious, it gives you something like that. For a true signal at 0, this is the distribution of the maximum likelihood estimator. It looks like a Gaussian, it's actually not. It's some complicated product of an error function and exponential, and if the SNR was low enough, it would be ugly, and you shouldn't do Fisher. So let's go then to the little harder math. Again, my integral up here. Why is it really low dimensional? The thing to remember is that this inner product in the noise, the probability here for the noise, I can really write with respect to any basis. I can do orthogonal transformations. For simplicity, I'm taking whitened noise, as you say technically, but it doesn't really matter. You could write everything in a more geometric way that doesn't need such considerations. Now I'm going to be projecting the noise to use a base to describe the noise that lies along the first derivatives of the signal and second derivatives of the signal, which are the ingredients that go into making this ML and this MLI. And so I start taking the derivative with respect to the first parameter, and then the second, orthonormalize. I want this to be a basis. And now the point is that above the d plus 2 times d, after I'm done orthonormalizing with respect to all the first and second derivatives, all the other noise components don't do anything for this integral. They just integrate out. It's just a Gaussian integral. They just give you a constant. They don't change what's happening, the game that's happening here. So I can rewrite everything. I can write this in terms of these noise components, and everything integrates out. Actually, the deltas help me integrate out even the components of the noise along the first derivatives, and I'm left with something that looks like this, where these are all components of that describe the derivatives in terms of themselves, that they're kind of triangular matrices that do that, and the integration is only along the degrees of freedom that describe the second derivatives, the derivatives that come into this matrix. With some massaging, this can be rewritten as something like this. There's a piece that really looks like Fisher, except you don't have parameters here. You have these delta h's, which are differences between the waveform that you're studying, let's say, and the true one. There are still Fisher matrices, and there's a correction, which is an integral over this second derivative degrees of freedom. And the nice thing is that this integral is actually pretty simple. It's just a Gaussian integral. You can do it numerically. And all you need to do is to know this matrix here, which is kind of like a second order Fisher matrix, products of all possible second derivatives. So this integral is d times d plus 1 over 2-dimensional. It's trivial numerically, and you need to start from these inner products, basically. So what you need is something like d to the 4th inner products. Once you have those, this integral is easy. As a check, if you kill off the second derivatives, so if your function is really linear in terms of parameters, you're left with this determinant. This integrates out. The determinants kind of cancels out the square root of these, and you're back to the Fisher matrix result. Also, as a check, one can do the numerical problem that I did by evaluating this integral numerically. And you can tell this is basically the same distribution, except it doesn't suffer from numerical error. So have we met the grand challenge with this formula? Well, for one thing, how do you use this? In 2 dimensions, you can just, again, you do a grid and you go evaluate that integral all the place. If you have more, you can do a Markov chain in the space of maximum likelihood estimators. At each point, you know the probability, so you can know whether to accept your moves. The usual Markov chain game, the Metropolis stepping criterion. So something like this. Sometimes the move is not accepted. You keep the same point, and so on. In terms of complexity, well, it's still a challenge. I mean, this definitely, it's not super cheap, but instead of being million by billion by billion, there's a d4th to the 8th, which is the number of inner products that you need. So even for 10 dimensions, this is about 1,000. Takes you back into the petascale, so which is, if you have a Tera computer, which you can buy, in a couple of hours you can do a problem like this. It's not the holy grail. And it's very parallelizable. All these inner products you can certainly do on different processors. So with this you have an exact estimate of the frequentist error. I think this can also be useful because it can be used to seed a Bayesian inference Monte Carlo for a given noise realization through data, because it has an idea of where the maximum likelihood can be in general for any noise. And also this distribution will include the secondary maxima, if there are any, because the maximum likelihood local condition is satisfied by primary as well as secondary maxima. So again, if you find this in a Russian book, come tell me after I've published it, and don't tell the referee. But really, I've shown this to a few people who do statistics and data analysis, and the usual approach is to start with Fisher and then kind of do perturbations of that. And I've done that also. Kurt has done it with Eina a few years back. But this is actually an exact technique that uses this transposing thing. Don't look for don't look for the estimator for your noise, but look for the noise for your estimator. And when I found it, I was a little happy, and these are the things that make one happy in our business. So this was it. Thank you. Yes.
But sometimes ratios and do one integral and then bam.
Give me an example.
It's frantically enough that
Yeah. I mean, what I can say is that the trick here is that the maximum likelihood of a distribution is really a local criterion. If you want to average over noise realization any Bayesian thing, it becomes much harder because those are all quantities that are integrated out, and normally you even need the evidence, so which is very difficult to evaluate. So once you try to put an integral around the Bayesian estimator and to switch the integrals, you have this problem of that integral at the denominator that kills you, unless it's trivial. So that's why it's a holy grail. It requires nights and a different time. That's what comes to mind from that. But maybe there's another rotation into imaginary axis that gives you something even cooler. So yeah, which one? The general or the implementation?
no, I think it goes up.
Oof. Come on. This is interesting. So this. That? Oh! Okay. This? Or the one before?
Yeah.
Okay.
I actually just wondering if there were an absolute value of the expression of the answer.
Oh, sorry, it's a denominator.
Huh?
This is a denominator. Sorry, it's a determinant. It comes from the Jacobian element, so it comes from the translation. Let's say between parameter land and signal land. So this is actually interesting because I looked for quite a while of an analytic expression. After all, it's a determinant of normal variables with just a normal distribution. So, and it's there are analytical results for given symmetries of the thing, of the expression that you're taking in there, but this is strange enough that I don't think there's any closed form expression. So, but numerically it's not a problem. I mean, and in fact you can see, the way you do it numerically, you can see it up there. So these were written in terms of matrices, but there these n of m are just normal variables. So you can just do a Monte Carlo drawing uncorrelated normal deviates up there. plug them in there and just average out the determinant. So if you do it for 10,000 points, it converges, and it's very quick because these are small matrices. They are 10 by 10 or 100 by 100 or so on. So it's and another thing you can notice there is that the Fisher matrix is formally SNR squared. Amplitude square of the signal. The other pieces are suppressed by 1 over SNR because the delta H at leading order, the difference between the estimated and the true waveform is of order 1 over SNR, just the errors. And the MIJ is also suppressed because 1m is distributed like the second order Fisher matrix, which is again 1 over SNR squared, so it's 1 over SNR. I think that's correct, yeah. So to lead in order, you just get the F. Determinant of the F goes down there. You can express these delta H's as the derivative times the error, and then you get back Fisher pretty much from up there. You turn those delta H's into partial delta H times the error, and you get 2 Fishers. One of them takes out the inverse, and you get the real Fisher. So if Fisher is singular, forget about it. But that's but it's not. I mean, if there are parameters that don't matter here, they just project out basically, and you can just leave them out of the integration. So yeah, that's all. Thank you.